You've used ChatGPT, maybe you've used Claude or Gemini as well. You've asked it to write emails, explain code, summarize documents, and at some point, probably in the middle of a conversation, you thought, how is this thing doing all this? I won't give you the usual marketing answer nor some answer like it's trained on internet or something. Let us get to know the actual answer. What is actually happening step by step when you hit the send and when it starts typing back. That's what this video is about. No math, no jargon, just real intuition. And by the end of the video, I promise you will look at AI tools completely differently. Let's start at the very beginning with what problem these models are actually trying to solve because it's not what most people think. Here's the thing that surprises most people. A language model at its core does exactly one thing. It predicts the next word, or more precisely, the next token. That's it. For example, feed it the Eiffel Tower is located in, and it predicts Paris with very high confidence. Feed it, she opened the door and was surprised to see, and it has to reason about context, tone, and story logic to predict what comes next. Same mechanism, but wildly different complexity. Now here's the wild part. This one simple task, predict the next token, when done billions of times across trillions of sentences, gives rise to a system that can write code, pass the bar exam, diagnose medical images, and hold a conversation. All of it emerges from the next token prediction at scale. It sounds almost too simple, but the magic is entirely in how it figures out what comes next, and that's what the rest of the video is about. To predict the next word well, the model needs to understand the words that came before, but computers don't understand words, they understand numbers. So the first step is converting language into something a computer can actually work with. Before the model reads a single word you've written, it breaks your text into chunks called tokens. And here's the first thing that surprises people. A token is not always a word. For example, type ChatGPT is unbelievable into OpenAI Tokenizer, a free tool that you can try right now, and you'll see it splits into 7 different tokens. The word unbelievable alone becomes 3 tokens. Common short words like is or the are usually 1 token. Rare or long words get chopped up. Why does this matter? A few reasons. First, it's why models sometimes struggle with spelling. They never really see individual letters, they actually see chunks. Second is, it's why longer documents cost more to process. You are billed per token, but not per word. And third is, different languages tokenize very differently. English is very efficient in that case. Languages like Thai or Arabic often need far more tokens for the same idea, which is part of why models perform better in English. And once your text is tokenized, each token gets converted into a unique number. Chat might be 14126, Paris might be 9458. The model never sees text again after this point. Everything from here on is numbers. But a raw number like 14126 carries zero meaning. Paris and London would just be two random integers, totally unrelated as far as the model is concerned, right? So the next step is to turn those numbers into something that actually captures meaning, and that's what embeddings do. So here's where it genuinely gets beautiful. Like each token number gets converted into what is called an embedding, which is a long list of numbers, typically hundreds or thousands of values, that positions that word in a high dimensional space. So think of it like a GPS coordinate, but instead of latitude and longitude in 2D space, you have 768 or 1536 dimensions encoding meaning. So for example, in this space, king and queen are close together because they are both royalty. Dog and cat are close because they're both pets. But here's where it gets wild. So you can literally do king minus man plus woman and you land almost exactly on queen. The model learns this geometry automatically just from reading text. Nobody programmed in royalty or gender, it discovered those structures on its own. And this isn't just a cute trick. This geometric structure is what lets the model reason about analogies, categories, and relationships. When you ask it what's the capital of Japan, it's partly drawing on the geometric fact that Tokyo sits in meaning space relative to Japan, the same way Paris sits relative to France. The embedding is also where context starts to matter. The word bank in the sentence I went to the river bank and the sentence I went to the bank to deposit money gets different embeddings because the surrounding words shift its positions in meaning space. This context sensitive adjustment is handled by the next mechanism. So basically now every word is a rich vector of meaning floating in space. The model has to read your entire input, all those vectors, and figure out how they relate to each other. That's the job of the transformer's central innovation, the attention mechanism. This is the concept that entire field pivoted on. The 2017 paper that introduced was literally titled Attention is All You Need. So what is attention? For every single word the model processes, attention answers one question. Given everything else in the sentence, which other word should I be paying more attention to right now? Let's take an example. Take the sentence that trophy didn't fit in the suitcase because it was too big. When the model reaches the word it needs to figure out what it refers to, the trophy or the suitcase. A human knows immediately if it was too big, it must be the trophy that didn't fit in. The model figures this out through attention. It assigns a high attention score between it and trophy and a low score between it and suitcase. Change the sentence to too small and suddenly it refers to the suitcase and the attention scores flip. Same sentence, same structure, opposite attention pattern. Mechanically, attention works by giving each word three things. A query, like what am I looking for? A key, what do I contain? And value, what should I pass on if I match? Every word's query gets compared against every other word's key, and the one matches well get the high score. And those scores determine how much of the word's value flows into the final representation. You don't need to remember Q, K, V. The intuition is this. Attention lets every word look around at the full context and decide what's relevant. Before attention existed, models read text left to right, word by word, with no ability to jump back and reconsider. Attention broke that limitation entirely. Now, here's the thing, one round of attention from one perspective isn't enough. The word it might need to track grammar in one direction, emotional tone in another, and spatial relationships in a third. The transformer handles this by running attention many times in parallel through what's called the multi head attention. So instead of running attention once, the transformer runs it multiple times in parallel, each time with different learned patterns. Each of these parallel runs is called an attention head, and each head learns to specialize in a different type of relationship. For example, researchers have actually probed what different attention heads in GPT style models attend to. Some heads track coreference, that is, who, it, or they refers to across sentences. Other heads track subject verb pairs, making sure the dogs pairs with run, not runs. Some heads seem to track positional patterns, attending to the token two positions back, almost like pattern matching shortcut. Some track sentiment, nobody assigned these roles, the model learned them from the data. All of these heads run simultaneously on the same input. Then their outputs are concatenated and combined into a single, much richer representation of each word, that is, one that encodes grammatical role, coreference, sentiment, and position all at once. This is why models are so much better at understanding nuance than anything that came before. A single perspective misses things, 8 or 16 perspectives running in parallel, each specializing naturally, that catches almost everything. So we have attention and we have multi-head attention. These operations happen inside what's called a transformer block. And the key inside of the architecture is that these blocks are stacked on top of one another, letting the model build deeper and deeper understanding with each layer. One transformer block, one round of multi-head attention plus some additional processing only gets you so far. So the architecture stacks these blocks vertically. The output of block 1 becomes the input of block 2 and so on. For example, GPT-2, the model OpenAI released in 2019, had 48 layers. GPT-3 has 96. Modern frontier models are estimated to have over 100. Researchers who probe what different layers do find a consistent pattern. Early layers pick up on surface patterns like capitalization, punctuation, common word pairings. Middle layers build syntactic structure like subject, verb, object relationships. Later layers encode semantic and pragmatic meaning, that is, what the speaker actually intends and what's implied but not said, basically emotional subtext. So think of it like reading a sentence yourself. Your first pass notices the words, your second pass understands the grammar, a third pass understands the point being made, a fourth pass understands whether the writer is being sarcastic or not. The transformer does all of this in one forward pass, layer by layer, in parallel, for each token simultaneously. Each layer only adds a small refinement to the representation, but stack 100 of them and you can get something that can understand Shakespeare, debug Python, and explain quantum mechanics in plain English. Now we understand the architecture, but an architecture is just a blueprint, a skeleton. What fills it in, what gives it actual knowledge and capability is training. And training is where things get truly massive in scale. Training is a process by which a transformer goes from a random pile of numbers to something that understands language. And the process is almost absurdly simple in concept. Show the model the beginning of a sentence, ask it to predict the next token. Check if it got it right, measure how wrong it was, adjust every weight in the network, billions of them, very slightly in the direction that would have made the prediction more correct, repeat for trillions of tokens. So this is an iterative process. GPT-3 was trained on roughly 300 billion tokens. That includes a large chunk of internet, books, Wikipedia, GitHub code, academic papers. The training run took months on thousands of specialized GPU chips running in parallel. The energy cost was equivalent to the yearly electrical consumptions of hundreds of homes. And that was in 2020. Frontier models today are trained to 10 times to 50 times more data with far more compute. What emerges from this process is remarkable. The model never had anyone explain what a metaphor is, or how to write a cover letter, or what the capital of France is. It learned all of it by compression, that is, by being forced to predict what comes next in billions of different documents. It had to develop internal representations of facts, grammar, reasoning patterns, and world knowledge. That is because those internal representations are what makes a prediction possible. Those weights, those billions of numbers, are the compressed residue of reading more text than any human could read in thousands of lifetimes. Also, training gives you a model that can predict text, but predicting text isn't the same as being helpful, right? A raw training model will complete your prompt, but it might complete how do I make someone feel bad in a genuinely harmful way. To get a useful, safe assistant, there's one more step. So, after base training, the model goes through fine tuning, where it's trained specifically on curated examples of good question answer pairs, but the real transformation comes from RLHF, reinforcement learning from human feedback. OpenAI employed teams of human readers who were shown multiple model responses to the same prompt and asked to rank them, which was more helpful, which was more accurate, which was less harmful. So those rankings were used to train a separate reward model that learned to predict what humans prefer. Then the base language model was fine-tuned using reinforcement learning to maximize that reward signal. The result was the jump from the raw GPT-3 to Instruct GPT, which was dramatically more useful despite being a smaller model. This is also where the safety behaviors come from. When a model declines to do something harmful or adds caveats or asks for clarification, that behavior was shaped by RLHF. Human raters flag certain types of responses as low quality, and the model learned to avoid them. The trade off is that RLHF can make models overly cautious or slightly sycophantic because raters tended to prefer confident, agreeable responses even when a more uncertain or pushback heavy response was actually more accurate. It's an active research problem in the field. All right, so we've gone from tokens to embeddings to attention to layers to training to alignment. Let's put it all together in one clear picture because understanding how these pieces fit in what gives you a real intuition for why models behave the way they do. So here's the full picture in one shot. You type a message, it gets broken into tokens. Each token becomes a vector in embedding space. Those vectors pass through first transformer block where every token runs multi-head attention, looks around at all the other tokens to update its own representation. That updated representation passes to the next block and the next and the next and so on. So all the way up to 96 to 100 layers. And at the very end, the model looks at the final representation of the last token, that is the most recent word in your input, and produces a probability distribution across its entire vocabulary. Maybe 50,000 possible next tokens, each with a probability. It samples from that distribution, and the token it picks gets appended to the conversation. Then it does the whole thing again for the next token and again until it decides the response is complete. The entire process for a response of 200 words might take half a second, and it's actually happening for millions of users simultaneously. Understanding the forward pass also helps you understand the limitations. That is why models hallucinate, why they lose track of long documents, why they get confused by complex reasoning. Those aren't just bugs. They are natural edges of what architecture can do. Here's the thing about hallucination that most people don't realize. It's not a bug the engineers forgot to fix. It's a natural consequence of how models work. For example, ask a model to cite a paper on a niche topic. It often generates an author name that sounds plausible, a journal that exists, a year that's reasonable, a title that's coherent, and none of it's real. Why? Because the model is not retrieving facts from a database. It is generating the most probable next token at every step. Smith et al. Sounds like a real citation. A plausible year follows, a plausible journal name follows. The model is always doing what it was trying to do, produce likely sounding continuations. It just has no internal fact checker stopping it when the likely sounding thing happens to be false. This is why grounding models in real time search results or in your specific documents helps so much. You're giving the model actual facts to attend to, so the probability distribution shifts towards the tokens that are actually true rather than merely plausible. And this is exactly why understanding the architecture matters so much. Once you know how it works, you know how to use it better and how to catch it when it's failing. Here's what you now understand that most people, including a lot of people who use AI professionally, don't. A language model takes your words, breaks them into tokens, converts them into vectors in meaning space, runs a dozens of rounds of attention across every layer, and at the end produces one token, the most probable next word, at a time. It has no memory between conversations unless you give it one. It has no internal fact checker. It doesn't know things the way you do. It has compressed statistical patterns from trillions of words into billions of weights. That understanding tells you when to trust it and when to double check it. It tells you why giving it more context makes it smarter in that moment. It tells you why it's better at common tasks than rare ones. And it tells you why it's genuinely impressive, not because it's magic, but because the scale and elegance of what it does with a single simple objective is actually remarkable. If this clicked for you, the subscribe button helps more people find it. And let me know in the comments what do you want to understand the next about how AI actually works. Thank you.